Hi, Gypsy. Sorry about the hiccup this evening. Tonight we're going to cover Module 10, at least part of it anyways. We'll say the last part for next week. So 10.1 is about the sampling distributions for sample means. Let's real quick review what we remember about the distribution for sample proportions. The sample proportion, which we denote with p hat. P hat is distributed normally with mean p, the population proportion, and a standard error of p times 1 minus p over n squared of all that. This is the mean standard deviation. If there are at least 10 expected successes and expected failures. Well, it turns out that the sample mean, where you're asking a numerical question instead of a yes or no question, also it can be distributed normally. So it would also be distributed normally, but its mean is now the same as the population mean, whereas before the p is the population proportion. And then so that's our mean, and then the standard error now is sigma over square root of n, where sigma is the population standard deviation, and is our sample size. Okay, but it always has that mean and standard deviation. When its normal is if the population is normal, or the sample size, that's n, is, I'm going to put here in quotation marks, large. So what do we mean by large? Well, it depends on how far the original population is from being normal. If you have a very, very skewed distribution, or a very tail-heavy distribution, you'll need a larger sample size. But in general, and a sample size of at least 30 is large enough for any population. So no matter how skewed the original distribution is, if your sample size is at least 30, then your sample mean will follow a bell curve, where the mean is the same as the population mean, and a standard error that is the standard deviation of the population over the square root of n. So similar to the sample proportion, with larger sample sizes, we get smaller standard errors, which means we get a better estimate for our population mean. Now, with the means, unlike with sample proportions, there's a different, a little different thing though that happens when we estimate that. So the problem is that we don't normally know what sigma is. So we substitute sigma, S for sigma. In other words, when we do if we went back and mirrored our confidence interval, 95% confidence interval for mu would be, instead of the x bar plus or minus 2 times the standard error, which would be x bar plus or minus 2 times the sigma over square root of n. Okay. So, but we don't know sigma. So put a little arrow there. I don't know what that is. So instead, what we do is we substitute. I'm going to put a little equals and put a question mark over that. We substitute S, which is the standard deviation of our sample. So that's the sample. S is the sample. Standard deviation. Okay, so the only issue with that is that it turns out that the error rate goes up. So in other words, when we do a 95% confidence interval, we expect to capture the population proportion or the population mean, in this case the population mean, 95% of the time. But it turns out, which means we miss it 5% of the time. But it turns out that if you just swap out the sigma for an S, you often, especially with smaller sample sizes, you miss your population mean more than 5% of the time with your confidence interval. So what happens is we need to fudge the 2. We need to change it. And remember that 2 was really, it's a z-score. More accurately, it was 1.96. But it could change depending on your confidence level. We sometimes, if we use a 90% confidence level, it was 1.645, or if we used a 99% confidence level, it was 2.576. Now, of course, you didn't have to use those because those were done by the calculator if you use your calculator, but it's still something to keep sort of in the back of your mind in terms of how far out do I need to go to get 90% of the data, or 95% or 99%. Well, if I substitute sigma with S, then I have to go out further. How much further depends on the sample size. The bigger the sample size, the more accurate estimate I get. So I don't have to go out quite as much further. The long and the short of that is, in general, when you subtract the mean from an observation, and in this case our observation is our sample mean, and our mean is our population mean, and divide that by the standard deviation, which in this case is the standard error, that has a normal distribution, and in particular, it has a standard normal distribution. This is a z-score. Okay? But if we change that sigma to an S, then the distribution isn't quite normal anymore. It's a little more tail-heavy, in fact. How much more tail-heavy, again, depends on n. But this has a t, we say this has a t distribution, so we actually use the letter t to represent that instead of the letter z. We say this has a t distribution. With n minus 1 degrees of freedom. Now what is this thing, degrees of freedom? And why is it n minus 1 and not n? Well, it's a little bit complicated, but it goes back to the standard deviation formula way back in Module 2, using n minus 1 instead of n. And it has to do with the fact that your deviations have to add to 0. So if you know n minus 1 of them, you can add them all together, and the last one has to be whatever adds to that to make it 0. So if you know all but one of the deviations and you add them and the answer is 5, then the last deviation has to be negative 5 to add it, to make it add to 0. So only n minus 1 of them are free to vary, as it were. So there's n minus 1 degrees of freedom. There's more to it than that in the module, but really that's sort of the big thing that you need to know, is that in this module, instead of a z, we're using a t because we're substituting sigma with s. To give you a quick idea of it, what I'll do is I will bring up a new page here and show you something called a t-table, which, like a z-table, you're allowed to use on the test if you wish, but I don't necessarily recommend that. If I do t-table, PDF, I think the first one is just fine. Yeah, okay. So it gives, at the top, it gives the sort of the T label. But really, what you want to look at is the bottom where it says confidence level. Let me make this slightly bigger. Here I can take a green filter. Oh, no, that's worse. Never mind. Let's see. There we go, that's better. So if I go to 95% confidence interval, right down there, you'll see right above it is 1.960, which is the more precise z-score. Well, on the left, far left, is the degrees of freedom. And so you'll notice that that number goes up. That's the number in front, that's the number of standard errors. And it's actually not much bigger than 2, but if you want a more accurate answer, you need to use that number instead of 2 in front of the standard errors. When your degrees of freedom is very small, 1, 2, 3, you have to go a lot more than 2. But in that case, you need to make sure your population is fairly close to normal anyways to use a very small sample size. The population should be roughly normal. All right. So yes, this is sort of a pretty hardcore concept, but when push comes to shove, what you're going to do is you're going to use your calculator to find confidence intervals and to find and to do hypothesis tests. So what I'm going to do then is do at least one example of each. So let's go back to the OLI notes. And really that's more or less what you need to know for topic 10.1. So let's pick an example in 10.2. Okay. And this is the concepts, but what we're going to do is let's see here. Oh, here we go. And in this case, actually, they make an assumption about this sigma. So let's not do this example. My apologies. Let's go on to the next answer. Next question. Confidence interval. Okay, so here's the T model. And so, all right. So we got a cable. A group of engineers developed a new design for a steel cable. They need to estimate the amount of weight the cable can hold. The weight limit will be reported on cable packaging. The engineers take a random sample of 45 cables and apply weights to each of them until they break. The mean breaking weight for the 45 cables is, and there's the mean, standard deviation is, and then they give you a standard deviation. So what we're going to do is we're going to do a 95% confidence interval. Well, let me show you how to do that on the calculator. All right, so let me clear this out. So you hit the Stat button, and then you go over to Tests, and again you have to go down. But when you get down, you don't have to go down too far. It should be number 8, I believe. T interval. So instead of Z interval, we use a T interval. So when you want to do a confidence interval for a mean, it's just a T interval. So you do number 8. Now, this is a little different than what we saw with proportions. The first question asks whether we want to do our input as data or statistics. Data would be if we had the breaking weights for all 45 of the cables in a list. We don't. We have the summary statistics for the sample. So I go over to stats and I hit enter. And now I get a different slate of choices. But those are all things I have. I get the X bar, the mean, that's 768.2. So I just type that in, 768.2. I go down to the S subscript X, it's just the standard deviation. I put in the S, is 15.1. And then the sample size was 45 cables. Confidence level is already there, and I just hit calculate. And it gives me my confidence interval. So roughly my confidence interval is, if I round, is about 763.7 pounds to 772.7 pounds. So we're 95% confident that the mean breaking strength is within that range. Okay. All right. So, and I assume they have their answer down there somewhere. There you go. 763.7 to 772.7. So the mean breaking weight should be somewhere in that range. So, and again, as this says here, you can use other confidence levels, but that's as simple as changing the C level on the calculator. Here's another example. We'll do this one on the calculator. Now we have a sample size of 71, and we have a mean number of alcoholic drinks of 3.93 per week, and a standard deviation of 3.78. This is pretty clearly non-normal, because just one standard deviation below the mean, you run into 0, just over standard deviation, and you can't have negative numbers of alcoholic drinks per week. So I know that this is not going to be a normal distribution, but I go to my calculator and I say stat, and I go over to tests, and I can just hit 8 if I remember that that's a t interval. And now I just need to change my sample mean, which was 3.93. 3.93. Standard deviation, I can see on the screen here, is 3.78. And the sample size was 71 students, which means that my sample is plenty big enough, that's well over 30, that I can use the normal distribution of the t-distribution. The requirements for using the t-distribution are the same as the normal distribution. And now I see that we can be 95% confident that the mean number of alcoholic drinks per week for all college students is somewhere between 3.04 and 4.82 drinks per student. And so I assume that's down there somewhere. Yeah, it's oh, no, what was it? Let's bring my calculator back up. 3.04 to 4.83. Oh, they did the 90% confidence interval. Sorry, that's why I can't find my answer. But if I wanted to do that, I wouldn't have to change anything else, but go to stat, tests, number 8, and go down and change the C level to, and change that to 0.90. That's going to actually just change to 0.9. And now I see that that's 3.18 to 4.68. And I see that's the second answer. And now it tells me, there you go, that was good. All right. All right, so I mean, that's pretty much it for confidence intervals. So now let's go to hypothesis tests. So all of this stuff is really analogous. It's just now we're talking about the mean, some mean in the population instead of a proportion of the population. Okay, so let's kind of pick a middle page here. We may lose some of the background. Actually, matched pairs. Let's not do that one yet. Let's go back to page 2. We'll talk about matched pairs in a minute. All right, so all right. Maybe the hypothesis test was on the very first page. So I think it looks like the second page is more talking about some of the information. All right, here we go. Cell phone data. All right, cell phones and cell phone plans can be very expensive, so consumers must think carefully when choosing a cell phone and service. This decision, blah, blah, blah. All right. Melanie read an advertisement from the cell phone giant, CPG, for short. She thinks it's too good to be true. The ad states that customers in Los Angeles get an average data download speed of 4 megabytes per second, which is pretty fast. With this speed, the ad claims it takes, on average, only 12 seconds to download a typical 3-minute song from iTunes. Only 12 seconds on average to download a 3-minute song from iTunes. Melanie has her doubts about this claim. So she gathers data to test it. So she asks a friend to use the network to download a song, and it takes 13 seconds to download it. Well, that's more than 12, but that's not evidence. So what she does is she has the friend do it several times, and she gets a mean download time of 13.5 seconds for her sample of downloads. So how would that work as a hypothesis test? Oh, sorry. Let's take a look and talk about what our hypotheses would be in terms of how she did this. Okay. Well, we still, just like before, we still have a null and an alternative hypothesis. We have HO which is mu equals something. Now it's about the population mean. Instead of being about P, it's about mu. And then HA is that mu is, and then that it's greater than, less than, or not equal to. Well, what's the company's claim? Well, that it should take an average of 12 seconds to download a 3-minute song. And she doubts this. She thinks that it actually takes longer, which would be greater than 12 seconds. So those would be her null and alternative hypotheses. Okay? And that's all we can do so far from the information that's given. Let's look at what else. So we have a sample mean, but it doesn't actually give a sample size yet. We also don't have a sample standard deviation. So we actually don't have any information. But there's the HL and HA stated in terms of mu, and that's exactly what we did. Mu equals 12 and mu is greater than 12. Okay. There's no reason to think that download times are normally distributed. So the sample has to be large, and the sample has to be random. No one decides to use one phone, but randomly select status, times, and locations. So she did 45 downloads, and she also got, right there, that's her N, and she got a sample standard deviation of 3.2 seconds. So now we can use the calculator to get our p-value. So we get a stat, we get a test, and this time it's a t-test instead of a t-interval, because we're doing a hypothesis test. So t-test, I'm still using data. My mu0 is the mean in my null hypothesis. That's HO, which is 12. Okay. Yep. What's up? Gypsy. What keys? What do you mean, what keys? Where did I mention keys? Oh, on the calculator. Sorry. Stat, edit. Stat and test again is what you want. Stat and tests. So, same place as the hypothesis. All the hypothesis tests and the confidence interval are under stat button. There's your stat, edit, etc. And then go to the test heading. And now it's not. And so for a confidence interval for a mean was t interval, but for a hypothesis it's t test number 2. Okay. All right, and then so mu0 is 12, and then her sample mean it said was 13.5. That is more than 12, but let's see if it's enough. Oh, I didn't put that in the right slot. Mu0 is 12. Go down, and then x bar was 13.5. And then it says the standard deviation was 3.2, and the sample size was 45. And we did want to test that the mean was greater than 12, so my alternative hypothesis is already correct. So those are the things I want to enter into the slots, which is really just filling in the blank from information in the problem. I didn't have to determine any of those numbers. I just had to find where they were in the problem. And then hit calculate. And the p-value there is very, very small. 13.5 seconds doesn't seem like a lot more than 12 seconds, but because of the fairly small standard deviation and decent sample size, the p-value comes out very small. And then the test statistic is the t. So if you're asked for the test statistic, that's in this case t equals 3.14. So let's put that down. Okay, so test statistic. So before, with proportions, the test statistic was a z, but now it's a t. So t is approximately 3.14. And then the p-value was approximately 0.001, I think. Okay. Calculator, that's what I wanted. Yeah, 0.001. I could say 0.0015, but by the way, it's a very small p-value. Okay. Well, I didn't specify a significance level, but that is certainly the strongest significance level that we commonly use is a 1% significance level, meaning that if we get results that would occur less than 1% of the time, less than 1 time in 100 by chance, that causes us to believe that the alternative is actually true instead of the null hypothesis. So in this case, my conclusion would be that there is very strong evidence to say that the mean time to download a 3-minute song is more than 12 seconds. I mean, I could, of course, I should probably have added on CPG's network. In fact, I will on the CPG network. And then, as I've mentioned before, I almost always put my p-value at the end of that sentence. So what that does is it allows the reader to make their own judgment about the strength of the evidence. Just, I said there's strong evidence. Well, how strong is it? The p-value is how strong that evidence is. So that's a hypothesis test for a mean. We'll look at least one more, but that's basically it. You have to determine your hypotheses, and once you have your data, make sure that the sample is gathered randomly, that it's at least 30, or that you can be pretty sure that the distribution is normal, and then go to your calculator to get the p-value and test statistic. All right. So on page 3, it talks about a similar type of a type of t-test that's called matched pairs. So let's talk about what matched pairs mean. With matched pairs, it means you have a natural pairing of the data. Oftentimes it's before and after, but what you're doing is you're comparing the same thing. You're taking 2 different measurements on the same individual. Sometimes it's you could take data from a husband and wife, and then the pairing is the measurement for the husband and measurement for the wife. And in those cases, you always look at the differences of the measurements. So even though you're taking 2 observations for each individual or each natural pair, once you subtract, you end up with just 1 set of data. So an example of this is drinking and driving. And what they did was they took 2 different drivers and measured their reaction time before and after drinking. I mean, drinking 2 beers. Okay, so not a huge amount because I imagine their goal was to show that even a small amount of drinking can impair your reaction times. And so they talked about negative differences, which most of them are, mean a slower reaction time after drinking the 2 beers. So we actually subtract that. The order of subtraction is not critical. You just have to keep it in mind when you do your hypothesis test. With the hypotheses, on a matched pairs test, these hypotheses you see here, the first one, is always the case, that the mean is equal to 0, because what you're saying in that case is that the difference, there is no difference, is what that means, because the mean is the mean of the differences. And then the alternative depends on your question. Since we say slows reaction time, well, as it says here, a negative means the person has a slower reaction time, so we would say nearly less than 0 would mean a slower reaction time. That's our alternative hypothesis. So then they went through the data, and here's the data. But notice here's a key sample of 20 college students, and then it talks a little bit about that below, because that's less than 30. Well, there's actually ways to determine if the data are at least somewhat close to normal. And so even if you have a sample size, as long as it's not like 2 or 3 or 4 or 5, if it's kind of 15, 20 or so, you can do a test to see if the data are at least not heavily skewed as it says down here. And if that's the case, then you can do go ahead and do a t-test. And here's your histogram of the differences, and you can see that histogram is not terribly skewed. So rather than go through the way they do it, once again, here's our data. We would take our calculator, and we would go to Stat, go to Test, and go to t-test, number 2. But this time our mu0 is 0. Our difference is 0. Our x-bar, you can see over there, is negative 0.46. Oops, look at that. Oh, I'm still on the time. This is the other thing. There we go. Negative 0.46. And our standard deviation is 0.87. But our n was 20. And we're curious to see if the mean is less than 0. In other words, that there actually is a decrease in reaction times. Okay, so I changed it to less than, and then I go down and calculate, hit enter. So our p-value is 0.014, test statistic negative 2.36. Let's see, so the researchers set a significance level of 5%. And that p-value is less than 5%. 0.05% is 0.05. That p-value is 0.01. So that would mean we do have strong enough evidence to say that drinking just 2 beers does indeed slow the average reaction time. As we saw, there was at least one student whose reaction time was actually a little bit quicker after the 2 beers, but that could be an anomaly. So, all right. So that's pretty much it. If you can do confidence intervals, and you can do hypothesis tests on the calculator, that's the key, and that's really the key to what you'll see on the test and on the quiz. The only thing I'll mention on the test is there is going to be one question about the sampling distribution. We'll go back to that. That's the previous page. Okay. Right here. So, but what I might give you is I might give you the mean there, and I actually might give you that standard deviation of the population, and then ask you to calculate a probability about the sample mean. In other words, so, in fact, there might even be a question like that. So, I don't think this is on the quiz, but I believe there might be a question like this in the test. So let's take a look. Let's see if we can find something similar to that in OLI. Let's try those two. All right. Okay, here we go. So here we have a population of babies with a mean of 3,500 grams, standard deviation of 500 grams. We selected a random sample of babies to test our assumptions about the population. And it says, we saw previously, so actually let's go back to that page and look at that question, that example. So you can see what the results were and see how we would do this question on the calculator. There's a plain baby. All right, here we go. So this parameter is the 3,500 because that's for the population. We got 3,400. We're curious, is it unlikely to have a mean birth rate of as low as 3,400 grams? Well, there's a random sample. This is just 9 babies, so our if we go back into this, for that particular example, so we had a population. In this case, the population was distributed normally, so we don't need a large sample size. So X is the weight. This is weight of individual babies. And that's distributed normally with a mean of 3,500, standard deviation of 500. X bar, which is the sample mean weight of random samples of 9 babies Well, if the original population is normal, this is also normal, with a mean of 3,500, but the standard deviation or standard error is 500 over square root of 9, or 500 over 3. Well, 500 over 3 is, 3 doesn't go into 500, so I just leave it as 500 over 3. Okay? And so the question is, what's the probability that you'd end up with an X bar no higher than 3,400? Is that an unusual result? Well, since we're coming from a normal distribution, I can do normal CDF less than 3,400 means I can go all the way to negative infinity. Right? I have to stop anywhere, because this is a normal model. And then the mean is 3,500. Oops, we are in here. And the standard deviation. You don't even have to turn that into a decimal. You can just put 500 over 3. You can even put 500 over square root of 9. So let's see how unusual that result is. It said on the next page that it wasn't particularly unusual. Remember, normal CDF is second in the bars key, and then the second choice. So I'm going to put in a large real number, comma, 3,400, comma, 3,500, comma, 500 over 3, and I give an answer of approximately 0.27 or 27. No, that's just 27%. And what that means is 27% of all samples of size 9 will have a sample mean of 3,400 or less. So what that tells me is that's more than 1 in 4 samples have a sample mean that low. So that is not unusually low mean birth rate for sample size 9. There is a question, somewhat like that, on the test. So be aware of that. But if you can remember, basically the trick there, the one thing you have that students slip up on is they forget to take that standard deviation and divide it by the square root of n. That's not on the quiz, but it will be. There is one, I think, 1 or 2 questions. I think it's similar to the last test where one question is what's the mean versus the population mean? What's the standard error? And you take it, find the standard deviation, divide by the square root of n, and then it asks you a probability question. So you have to do a normal CDF with that mean that you just calculated and the standard error that you just calculated. So for 10.1 to 10.3, that pretty much wraps it up. Next week would be even faster. 10.4 will go fairly quick compared to even 10.1 to 10.3 since we started the section. But that wraps up what I wanted to say. So if you have any questions, Gypsy, you may ask away. Is it next week? Uh-oh. Perhaps it is. If it's next week, then I guess 10.4 won't be on it. Hold on 1 second. Let me pull it up. Maybe 10.4 was supposed to be this week. I messed up. If not, that's not a big deal to skip 10.4. We can do that. We can pull the questions up the test if you choose to. Oh yeah, look at that. I wasn't supposed to do that module. 10.4. Well, 10.4 is not a big deal, and we'll leave it off on the test. So here's, but I will quick mention it because it is involved. There's a checkpoint on it. So let's real quick look at 10.4. And what I'll do is I'll just do enough to try to get you through the checkpoint at the end of the module, and then I will omit, I'll put an announcement up, but I'll omit the 10.4 checkpoint from consideration. All right. So basically 10.4 is kind of like Module 9 in that it compares two population means. So you're looking at a mu1 and a mu2. In terms of the sampling distribution, you do exactly what you did in the last module, and you take the difference of the two population means. Well, we estimate that by the difference in the two in sample means from the two samples. They don't have to have the same sample size. Well, that will follow similar to what we had before, a normal distribution with a mean of mu1 minus mu2. And this is a nasty standard error formula, which I'm not even going to bother to put here. Because you're going to do anything you would do on the calculator. Confidence interval, I'll show you that real quick. So the confidence interval, if you go to stat and tests, and you see a two-sample t-test, it's the same thing for intervals. It's two-sample t-interval, it's 0. And to do it, you just put in the mean, standard deviation, and sample size for sample 1, and the mean, standard deviation, and sample size for sample 2. Confidence level, pooled, always leave no, and calculate. The default is no, so you don't have to do anything. So mean, sample standard deviation, sample size for each sample, and out will pop out your your confidence interval. And negative values means mu2 is bigger, positive values means mu1 is bigger, or at least we believe anyways, in terms of the confidence interval. So if we go back and we look, 13.4. So estimating the difference is the last part, and that's because it's oftentimes we just go ahead and do a, and this is also, by the way, a P that we often do a hypothesis test. Alright, so let's see here. Here we go. So we did calories in context. Mean number of calories purchased by women eating with other women, and mean number of calories purchased by women eating with men. And you see for the sample 1, women eating with other women in that sample, they ate more calories, or they bought more calories than they did when they were eating with men. Alright, so if I wanted an actual confidence interval, I'd take my calculator and go back up to the top. And X bar 1 would be 850. Standard deviation 1 would be 252. And N1 would be 45. X bar 2 would be 719. SX2, the second standard deviation is 322. And the second sample size is 27, close enough to 30, but it's probably not so drastically nominal that that's a problem. We'll go back to a 95% confidence level. And what pooled means is you want to assume they have the same standard deviation. It's always safest to say, no, I don't. Especially in this case, the standard deviations were pretty different, and then hit calculate. So what this is saying is, we can be 95% confident that women eating with other women, that the mean number of calories they purchase is between 15 calories less and 277 calories more than women eating with men. So, notice that 0 is included in that interval, which means for the confidence interval, it doesn't eliminate no difference as a possibility, which would be a difference of 0 if we have positive numbers. And then they do a 90% confidence interval, which does not include the 0. So, and then they said 95%, so that's an error there. They say we are 95% confident here, but then up here it says 90% confidence interval. So they do the data for a 90% confidence interval, so that's a little bit of a mistake. All right, so oops. Oh, sure. Let's bring up the count. Well, here's the errors. It says we are 95% confident that at Indiana University of Pennsylvania, undergraduate women eating with women order between 9.32 and 252.68 more calories than undergraduate women eating with men. And actually, they should talk about an average. There's also a weakness with that statement in terms of they don't mention the average number of calories. So I would change this to, and let's bring up my calculator because I actually want to use those numbers anyway, since it's supposed to be 95% confidence. I'd round it to the nearest calorie because that's more than accurate enough. I would say we can be 95% confident that at Indiana University of Pennsylvania, undergraduate women eating with women order between, on average, order between 15 calories less and 277 calories more than the average of women who are eating with men. So it's about the difference in the means. And they don't actually mention that in that statement. So, all right. Okay. What about a hypothesis test? A hypothesis test is easier to understand in this context than the confidence interval, because a hypothesis test is, and I would look at these hypotheses on the far right here. The null hypothesis is always no difference, that the two means are equal, and then the alternative is less than, greater than, or not equal to. So let's look at an example. So here's the we'll do the same data, but we'll do it in terms of a hypothesis test. So if we here, our hypothesis would be that the two means are equal, our null hypothesis. Our alternative would be that mu1, women eating with other women, order more calories on average than women eating with men, where mu1 is the mean number of calories ordered by women eating with women, and mu2 is the mean number of calories ordered by women eating with men. Alright, so, and that's what they did there. So then we have our data, and we actually have so they go through this complicated thing with the t-test, but that's why it's good we have the calculator. We have stat, tests, and we're going to use choice 4 now, the two sample t-test, because we have two independent samples. So we go here, look, all of the data are already in there because it remembers all that data. And so I put it right down. And I actually don't even have to put in the null hypothesis this time because it knows the null hypothesis is mu1 equals mu2. So in this case, we think that mu1 was the mean for women eating with women. We think that's greater than mu2, but it might be greater than mu2, the mean for women eating with men. Alright, full no again, calculate. And our p-value is 0.039. So this is below 5%, so if our significance level, what it say? significance of 0.05, then we could reject it. It's not much less than 0.05. Now, a very logical question might be, well, the p-value was 0.0385, but the 95% confidence interval included 0. Isn't that a contradiction? In other words, the p-value says reject no difference, but the confidence interval says no difference is a reasonable answer. So we get a p-value of 0.03, whatever it was. Well, what happened here was the p-value that greater than means it's a right tail. So that means that this is 0.0387. So we'll say 0.039. So that right tail area is 0.039. Well, when I do a 95% confidence interval, that's 95% in the middle. Well, that's 2.5% on each tail. So in effect, this would be equivalent to a p-value of a right-tailed p-value of 0.025, which is why. So this would be like a significance level of 0.025. So that's why in the uppercase, 0.039 is enough to reject at a 5% significance level, but a 95% confidence interval actually contains 0. A 5% significance level, so 5%, and this is important, one-tailed significance level is equivalent to a 90% confidence interval, because 90% would be 5% on each side, which is 10%, and then 90% in the middle. So that's why those two things are equivalent. You sort of have to, the pictures are the easiest way to understand that. It's a little bit tricky. But that should be enough for you to get the checkpoint, especially the end of module. I won't count the module for 10.4 checkpoint, since I didn't include 10.4 in the quiz. And the assignment sheet only says 10.3. Alright. Anything else? I think that pretty much wraps. Now that does wrap up what I wanted to say about the module. I think that I realize now, I remember why I did that, but I'd forgotten that I did it, was that in the past students don't like having test 3 and final exam on 2 consecutive weeks. So I pushed test 3 a week earlier, but it meant putting all of module 10 in 1 week. But I did that in the previous semester, but and left the pacing schedule that way, but forgot that I was doing the assignments. But it'll be to your benefit, because 10.4 won't be on test 3, and also 10.4 won't. I won't require you to do the 10.4 checkpoint, although I will require the module 10 and the module checkpoint, which will have it. All right. Anything else, Gypsy? Any questions about anything else? Okay, no problem. And if you have questions, post them to after, and I'll do my best to answer them. All right, take care. I'll talk to you soon.